All right, let's jump straight into this explainer. Chemistry often gets a bad rap as this messy, chaotic collection of random reactions. But honestly, it's more like a highly structured game. And just like any good game, it's played with specific, unbreakable rules that scale all the way from tiny, invisible atoms up to massive electrical reactions. So let's crack open that rulebook.
Here is our roadmap for today. First, we'll cover the basic language of chemistry. Second, decoding the periodic table. Third, understanding acids and bases. Fourth, redox, where we trade electrons. And finally, number 5, the sheer magic of electrolysis. Quick and painless, let's go. Section 1, the language of chemistry. Before we can start mixing things up in a beaker, we really need to nail down how elements actually talk to each other and combine.
And it all comes down to a concept called valency. Essentially, valency is just an atom's combining power. You can think of it as how many hands an element has available to hold on to other elements. Groups 1 through 4 can make 1 to 4 bonds, respectively. But then you look at Group 8, the noble gases, they have a valency of strictly 0. They're perfectly happy riding solo and literally don't make any bonds at all.
So, writing a chemical formula is basically just following a simple 3-step dance. Step 1, always write the metal first. Step 2, bring in the nonmetal but change its ending to "ide." So, sodium and chlorine become sodium chloride. Simple, right? And step 3, to balance the bonds, you just look at their valency numbers and swap them to figure out exactly how many of each atom you need. Easy. Moving on to Section 2, decoding the periodic table. It's so much more than just a list of elements. It's basically the ultimate cheat sheet for predicting chemical behavior.
Take Group 1, for example, lithium, sodium, and potassium. Notice how as you move down the column, we keep adding more and more electron shells. This physically pushes those outermost negative electrons further and further away from the positive pole of the nucleus. Since they're so far out, they're way easier to lose. And here's the kicker. The easier it is for a metal to lose that outer electron, the more aggressively reactive it becomes.
Okay, on to Section 3, understanding acids and bases. These are the absolute main characters in water-based chemistry, and they're defined entirely by the unique ions they release. Acids pump out positive hydrogen ions, while bases release negative hydroxide ions. These are the heavy hitters you definitely want to commit to memory. For strong acids, we've got the classics: sulfuric, nitric, and hydrochloric. Then there are weak ones like ethanoic acid, which, let's be real, you probably just call vinegar. On the flip side, we have our powerful alkalis, like sodium hydroxide and potassium hydroxide. Knowing these formulas by heart is totally crucial for understanding how the rest of our chemical story unfolds. Section 4, redox, which is really just trading electrons. Let's see how these elements interact when they get down to business. Listen, if you remember absolutely nothing else from this explainer, you've got to remember this cheat code: oil rig. Oxidation is the loss of electrons, and reduction is the gain of electrons. It perfectly locks the concept into your brain. In every single redox reaction, if one element is losing electrons, another is gaining them. It's a package deal. They always happen together. Let's put on our detective hats and apply this to a real-world scenario, making table salt from sodium and chlorine. If we follow the money, or, the electrons, we can clearly see the sodium metal losing electrons to become a positive ion. So it's getting oxidized. Meanwhile, the nonmetal chlorine happily scoops up those exact same electrons to become a negative ion, meaning it's reduced. Loss is oxidation, gain is reduction. Boom! Oil rig in action.
All right, Section 5, the magic of electrolysis. This is where we stop waiting for elements to trade naturally and literally force them to do it using raw electricity.
But before we start wiring anything up, here's our next essential rulebook mnemonic: panic. Positive is anode, negative is cathode. Trust me, when you're dealing with electrical circuits and chemistry, this ensures you'll never, ever forget which pole has which charge. Okay, so before we flip the switch, let's set the stage. Our electrical liquid circuit needs a few key players. First, inert electrodes, usually graphite or platinum, so they don't mess with the reaction itself. These get dunked into an electrolyte, which is just an ionic compound that's melted or dissolved so its ions can freely swim around. And, thanks to panic, we know our positive anode and negative cathode will pull in those negative anions and positive cations. It's literally the oldest rule in the book: opposites attract. The positive metal cations absolutely rush toward the negative cathode on the left to gain electrons.
At the exact same time on the right, the negative nonmetal anions flock to the positive anode to lose theirs. We are using pure electricity to rip this compound apart by dragging its ions to completely opposite sides of the beaker. It's pretty wild.
Well, hold up. Things get a little spicy when water crashes the party. If you just melt a pure compound, electrolysis is super straightforward. But if you dissolve it in water, water actually splits into its own positive hydrogen and negative hydroxide ions. Suddenly, we've got a massive competition at both electrodes, and we need some new rules to figure out who actually wins.
Let's check out the positive anode first, where the negative ions are duking it out. It's purely a numbers game here. If your solution is super concentrated with halide ions, like chloride, they win hands down and bubble off as a halogen gas. But if it's super dilute, meaning it's mostly just water, then water's hydroxide ions win the race, and you end up getting pure oxygen gas instead. Now, over at the negative cathode, it's all about hierarchy. Positive metal ions are competing with water's hydrogen ions, and this reactivity series acts as our ultimate judge. Notice exactly where hydrogen sits on this list. Right there in the middle, sandwiched between lead and copper. Its exact rank is the key to the whole shebang.
Here is the cathode rule. The least reactive ion is the one that gets discharged. Think of it like a brutal game of musical chairs. The highly reactive, aggressive metals like sodium or potassium, they fiercely demand to stay dissolved as ions. Because they refuse to leave, the humble, less reactive hydrogen gets kicked out. So if your metal is above hydrogen on that reactivity list, you're not getting metal at the cathode, you're getting bubbling hydrogen gas.
Let's watch all these rules come together in one glorious reaction, the electrolysis of brine, which is just really, really salty water. At the positive anode, the highly concentrated chloride beats out the hydroxide, bubbling off as chlorine gas. Over at the negative cathode, that highly reactive sodium absolutely refuses to be discharged, so hydrogen loses the fight and bubbles off. And what's left swimming in the beaker? The leftover sodium and hydroxide ions, which perfectly pair up to form sodium hydroxide, a seriously powerful alkali.
So, what does this all mean for us? Mastering this chemical rulebook isn't just about passing some exam. It's absolutely crucial for our future. Knowing how to manipulate ions, trade electrons, and force those exact trades with electricity is the literal blueprint for engineering tomorrow's energy. It's the foundation for everything from the battery in the smartphone you're holding to the massive, sustainable grid storage we desperately need. The rules are set. The real question is, how are you going to use them to engineer the future? Thanks for joining me on this explainer. I'll catch you next time.